In linear algebra, we define the concept of linear combinations in terms of vectors. But it is actually possible to talk about linear combinations of anything as long as you understand the main idea of linear combination. It is not hard to prove, and it is fundamentally important part of linear algebra. You probably see this before, but what do the product of vectors and matrix mean? The statement is if you got a matrix A with the m column, and we got a vector, and we know the product Ix is well defined. The product means there is linear combination of vectors A1 into An, where each vector multiplied by scalar. This is what the X mean, the linear combination of the column, the A, where you pick up precisely how much of each column present using the vector X. Let's prove it, starting with the definition. What's the object Ix mean? I1 matrix. Because we assume that A is m by n matrix, and each of the A1, A2, An vectors, they're all m by 1 matrices, or vectors if you like. So it makes sense, at least it is possible, that Ix could be equal to the combination of X. Where the things on the left and the things on the right are the vectors are the same size. So if you got two vectors the same size, or two matrices with the same size generally, and you want to prove they equal, then you said all the entries are equal. What can I do? Take Ix and compute I entry in terms that it's equal of the I entry of the right hand side. Yes. And if you want to be real formal and treat vectors like matrices, then treat vectors like matrices, and you don't get confused. We know that Ix is m by 1 matrix. That means that column index is equal to 1. Let's put this column index. So we treat Ix as a matrix now. I1 entry we take from definition of matrix multiplication. Okay. G1. Okay, I think about X here as a matrix. It is column vector, and the column vector index is always 1. I can write the explicit expression of these things because I know what they are. The J entry of the vector X is just a number. Yes? Okay, and what is Aij entrance of the matrix A? So Aij is taken a vector or column Aj and picking up the I entry. Yeah, the flipping between vectors in matrix notation is crucial. So Now I have statement about vectors, and we know the vectors special examples of matrix. And we know everything what happened with matrices when we add them, when we scale them by real numbers. And the answer was that you do everything by entry-wise. If I think about that I entry, of this vector here, we're taking vector aj here and multiply by number xj. And what is I entry is just precisely the definition of how we multiply the vector by scalar, and we do it by entry-wise. Wise multiplication. Okay. And then we define addition. Then we define addition. Addition xj, ij is a vector, and I'm looking at some I entry of that, and I know by definition of how I add vectors, or more generally matrices, and I do it entry-wise. And why it doesn't make sense going backwards is because I define some vectors or some of matrices to be an entry-wise, meaning that if I got two vectors and I want to add them together, how do I do that? I just make a new vector where each entry is the sum of corresponding entries in two vectors I started with, or more generally in vectors. This is entry-wise addition. Okay. That is why the steps make sense. First, how we multiply vectors by numbers, and second, how we sum them together, more generally vectors together. So now, what have I got? This sum is sum of ij, length m column vector, and we can interpret it as a matrix with one column. Yeah. And what I have shown, I shown that I1 entry, yeah, equal to I1 entry. Okay. So matrices AX and this sum matrices AX, and this sum have to be equal because all entries are equal. Okay. Having the one entry is too formal. It is useful in very first step when you apply the definition of matrix multiplication, but the one here is essentially not important. Not doing anything. So just proving this theorem.